Yes, it is practical to have a disconnect located between the utility service conductors and the meter. This type of arrangement is common in areas with high flood risks, where it is necessary to elevate electrical components above the flood elevation. The National Electrical Code, or NEC, does not specifically prohibit the use of a disconnect between the utility service conductors and the meter. However, the NEC does require that the disconnect be accessible and operable. In areas where the local electrical code is more stringent than the NEC, it is important to check with the local authority to ensure compliance. Yes, it is realistic to install a disconnect between the utility service conductors and the meter in areas with high flood risks. This type of arrangement can provide an additional level of safety and protection in the event of a flood. Here are a few considerations. The disconnect should be located where it is easily accessible for maintenance and repair. The disconnect should be designed to withstand corrosion and moisture. The disconnect must be rated for the voltage and current of the electrical service. It is important to coordinate with the local utility company to ensure that the disconnect is compatible with their equipment and procedures. It is realistic, practical, and legal to have a disconnect located between the utility service conductors and the meter in areas with high flood risks. This type of arrangement can provide an additional level of safety and protection in the event of a flood. Let's delve deeper into the technical aspects of installing a disconnect between the utility service conductors and the meter, especially in flood-prone areas. Firstly, understanding the National Electrical Code, or NEC, requirements is paramount. While the NEC doesn't explicitly forbid this arrangement, several articles indirectly influence its implementation. Secondly, accessibility is a key consideration. NEC Article 110.26 dictates requirements for access and working space about electrical equipment. The disconnect must be readily accessible for inspection, maintenance, and operation without requiring the removal of permanent structures or finishes. Thirdly, the disconnect's environmental suitability is crucial, particularly concerning corrosion protection. In flood-prone environments, electrical equipment is exposed to moisture, corrosive substances, and potential submersion. Therefore, the disconnect enclosure must be NEMA 4X rated or equivalent, providing protection against corrosion, water ingress, and ice formation. Fourthly, the disconnect's electrical rating must match the service's voltage and current demands. Select a disconnect with an amperage rating equal to or greater than the service entrance conductor's ampacity. For voltage, ensure the disconnect's voltage rating exceeds the system voltage, typically 120 volts, 240 volts, 208 volts, or 480 volts depending on the application. Fifthly, coordination with the local utility is indispensable. Utilities have specific requirements for service connections and metering equipment. Consult with the utility company to ensure the disconnect's placement and specifications align with their standards and do not interfere with their equipment or procedures. Sixthly, consider surge protection. Installing a surge protective device, or SPD, in conjunction with the disconnect can safeguard downstream electrical equipment from voltage surges caused by lightning or utility switching operations. Choose an SPD with a suitable surge current rating and voltage protection level appropriate for the location's risk profile. Seventhly, grounding and bonding are critical for safety. Ensure the disconnect enclosure is properly grounded according to NEC Article 250. Bond the neutral conductor to the enclosure at the service entrance to establish a low impedance ground fault current path. Eighthly, overcurrent protection is essential. The disconnect should be equipped with overcurrent protection devices, such as fuses or circuit breakers, sized appropriately for the connected load. These devices protect against overloads and short circuits, preventing equipment damage and potential fire hazards. Ninthly, consider the disconnect's location relative to the design flood elevation, or DFE. Electrical equipment installed below the DFE must be flood-proofed or elevated above it. In a scenario described, where the weatherhead is 25 feet above grade and the DFE is 8 feet above grade, locating the disconnect 12 feet above grade places it above the DFE, mitigating flood risk. Tenthly, labeling and signage are important for identification and safety. Clearly label the disconnect with its purpose, voltage, and amperage rating. Install warning signs indicating the presence of electrical equipment and potential hazards. Firstly, selecting the right type of disconnect is important. Several types of disconnects are available, including fused disconnects, non-fused disconnects, and circuit breakers. The choice depends on the application's specific requirements and preferences. Secondly, wire sizing and conductor selection matter. Ensure the service entrance conductors and the conductors connecting the disconnect to the meter are properly sized according to NEC Table 310.16, based on the ampacity of the service and the conductor's insulation type and temperature rating. Thirdly, conduit in raceway systems must be robust. Protect the service entrance conductors and the conductors connecting the disconnect to the meter within rigid metal conduit, or RMC, intermediate metal conduit, or IMC, or electrical metallic tubing, or IMT. These raceway systems provide physical protection against damage and corrosion. Fourthly, consider the available space for installation. The disconnect requires adequate clearance for access and ventilation. Ensure sufficient space is available to accommodate the disconnect enclosure, wiring, and any associated equipment. Fifthly, inspect all connections thoroughly. After installing the disconnect and making all electrical connections, inspect each connection to ensure it is tight and secure. Use a torque wrench to tighten connections to the manufacturer's specified torque values. Sixthly, test the installation meticulously. Before energizing the service, test the installation using appropriate testing equipment to verify proper operation, grounding, and insulation resistance. Perform a continuity test to ensure all grounding connections are intact. Seventhly, document the installation comprehensively. Maintain detailed records of the installation, including drawings, specifications, and test results. This documentation is valuable for future maintenance, troubleshooting, and inspections. Eighthly, consider future maintenance requirements. The disconnect requires periodic inspection and maintenance to ensure its continued reliable operation. Establish a maintenance schedule to inspect connections, clean the enclosure, and test the overcurrent protection devices. Ninthly, train personnel on safe operating procedures. Ensure that qualified personnel are trained on the safe operation and maintenance of the disconnect. This training should include procedures for disconnecting power in emergencies and for performing routine maintenance tasks. Tenthly, review local codes and regulations. In addition to the NEC, local codes and regulations may impose additional requirements for electrical installations in flood-prone areas. Consult with the local authority having jurisdiction, or OJ, to ensure compliance with all applicable codes and regulations. Firstly, consider the impact of voltage drop. Voltage drop can occur in long conductor runs, affecting the performance of electrical equipment. Calculate the voltage drop from the service entrance to the meter and ensure it is within acceptable limits, as specified in NEC Article 210.19a on Informational Note 4. Secondly, surge arresters should be mounted as close as possible to the equipment they are protecting. This minimizes the lead length and maximizes their effectiveness. Thirdly, using corrosion-resistant materials such as stainless steel or copper for grounding conductors and hardware can extend the life of the grounding system in corrosive environments. Fourthly, labeling the disconnect with a permanent, weather-resistant label ensures it remains identifiable even after prolonged exposure to the elements. Fifthly, regular infrared scanning of electrical connections can detect hotspots caused by loose or corroded connections. This allows for proactive maintenance to prevent equipment failure. Sixthly, consider the use of a ground fault circuit interrupter, or GFCI, for personnel protection. Installing a GFCI in the disconnect can provide additional protection against electric shock hazards, particularly in wet or damp locations. Seventhly, where possible, choose a disconnect with a visible blade design. This allows for easy visual confirmation that the disconnect is open, enhancing safety during maintenance and repair. Eighthly, consult with a qualified electrical engineer or contractor to ensure the design and installation of the disconnect meet all applicable codes and standards. Ninthly, when selecting a disconnect, consider the short circuit current rating, or SCCR. The disconnect's SCCR must be equal to or greater than the available fault current at its location to prevent equipment damage during a short circuit event. Tenthly, remember that proper torque is critical for electrical connections. Always use a calibrated torque wrench to tighten connections to the manufacturer's specifications to ensure a reliable and safe installation. Firstly, the location of the disconnect should not impede access to other essential equipment or pathways. Secondly, consider the aesthetic impact of the disconnect installation, especially in residential areas. Choose a disconnect enclosure that blends in with the surroundings and minimizes visual intrusion. Thirdly, ensure that the disconnect enclosure is adequately ventilated to prevent overheating. Proper ventilation helps to dissipate heat generated by the electrical components and prolongs equipment life. Fourthly, when routing conductors, avoid sharp bends and kinks that can damage the insulation and reduce ampacity. Follow manufacturer's recommendations for bending radius and support spacing. Fifthly, use appropriate wire connectors and terminations to ensure secure and reliable connections. Avoid using mismatched connectors or improperly crimped terminations that can lead to overheating and failure. Sixthly, consider the use of a surge counter to monitor the number of surge events that the surge arrestor has experienced. This can help to determine when the surge arrestor needs to be replaced. Seventhly, when working on electrical equipment, always de-energize the circuit and verify that it is de-energized using a voltage tester before touching any conductors or components. Eighthly, remember to follow lockout/tagout procedures to prevent accidental re-energization of the circuit while work is being performed. Ninthly, keep the area around the disconnect clear of obstructions and debris to ensure easy access and prevent hazards. Tenthly, regular inspections of the disconnect should include checking for signs of corrosion, damage, or overheating. Any issues should be addressed promptly to prevent further deterioration and potential safety hazards. Firstly, if the disconnect is located outdoors, consider the effects of sunlight exposure. Ultraviolet radiation can degrade the enclosure material and insulation over time. Choose a disconnect enclosure that is UV resistant or provide shielding to protect it from direct sunlight. Secondly, when installing a disconnect in a coastal environment, consider the effects of salt spray. Salt spray can accelerate corrosion and degrade electrical connections. Choose a disconnect enclosure and components that are specifically designed for marine environments. Thirdly, ensure that the disconnect is installed on a stable and level surface to prevent stress on the enclosure and connections. Fourthly, when drilling holes in a disconnect enclosure for conduit connections, use the correct size drill bit and debur the edges of the holes to prevent damage to the conductors. Fifthly, use appropriate sealing compounds and gaskets to prevent moisture from entering the disconnect enclosure. Sixthly, consider the use of a remote monitoring system to monitor the status of the disconnect and receive alerts in the event of a power outage or other abnormal conditions. Seventhly, when replacing a disconnect, be sure to disconnect the power and verify that it is energized before removing the old disconnect. Eighthly, remember to properly dispose of the old disconnect and any other electrical waste according to local regulations. Ninthly, keep a copy of the disconnect's instruction manual and wiring diagram readily available for future reference. Tenthly, encourage ongoing training and education for electrical personnel to keep them up to date on the latest codes, standards, and best practices. It's also crucial to remember that electrical work can be dangerous, and it should only be performed by qualified and experienced individuals. Always prioritize safety and follow all applicable codes and regulations.